All right, ladies and gentlemen, this is going to be review video 20, gas laws and how to use them. So in the last video, we talked about ideal gases, what they are, and then properties of gases. But in this video, you're going to learn about the different gas laws, what they say, and how to use them. So there's 6 that we're going to study on the whole. The first is called Boyle's Law. And Boyle's law states that pressure and volume are inversely proportional to one another, which means that as one goes up, the other goes down, and vice versa. The formula for that looks like this. We have P1V1 equals P2V2. And when you look at a formula with 1s and 2s in it, the 1s mean initial, so that's what you're starting with, and the 2s mean final, or what you are ending with. Right? So if I were to draw out a graph to represent this formula, knowing that those two things are inversely proportional to one another, my line on that graph would look something like this. Because I can see as I move to the right on my x-axis and I increase pressure, my volume is actually decreasing. And as I move up on my y-axis and I increase volume, my pressure is actually decreasing as I go in that direction. This over here is just a really quick graphic that kind of shows you a visual for that inverse proportionality, right? So you can see here, this volume is low. However, my little gas molecules in the middle here are bouncing all over the place, right? Like this one is going all over the place. That one's shooting in the corner. That one's bouncing off the walls. And the more force that those little gas particles exert on their container, the higher the pressure. But you can see when I increase the volume over here, now suddenly my arrows don't look so crazy. And yeah, these are still moving around. Obviously, it's a gas, but the arrows are a little bit less crazy. And so the pressure or the force exerted onto the sides of the container is a little bit lower. Charles' law states that volume and temperature are directly proportional to one another. And again, directly proportional means as one goes up, so does the other. As one goes down, so does the other. And this is the formula that you're going to see here. V1 over T1 equals V2 over T2. And again, the side on the left with the 1s is going to be your initial stuff. The side on the right with the 2s is going to be your final stuff. What you start with, what you end with. If I were to create a graph to represent that law, it would look something like this, because as I move to the right on the x-axis and I increase temperature, my volume goes up. As I move up the y-axis and increase volume, my temperature goes up. And that positive slope is reminiscent of that. So what we're seeing here in the graphic is over on the left-hand side, we currently have a low temperature. And as a consequence, my volume is also low, right? Because particles that are moving just a little bit, like they're moving, just not very fast, they don't need that much space. They're not going to put that much pressure on their container. But if I increase the temperature, suddenly those molecules are going to start moving faster. And if I want to keep my pressure constant, I gotta give them more room to move around. So my volume has to increase to keep that pressure constant. Gay-Lussac's law is going to state that pressure and temperature are directly proportional. So just like Charles' law said that volume and temperature were directly proportional, pressure and temperature are also directly proportional. Again, meaning that as one goes up, so does the other. As one goes down, so does the other. Our formula for that is going to be P1 over T1 equals P2 over T2, with my initial side on the left and my final side on the right. My graph for this one is going to look very much like the graph for Charles' law, representing that direct proportionality. Over here, we can see that on the left, I do not have a very high temperature. My temperature is low. As a consequence of my temperature being low, that means that my particles aren't moving very fast. They're just moving a little bit. and they are not putting a lot of pressure on the side of that container, so my pressure is also low. But if I heat it up and I make my temperature high, suddenly those particles are going to move a ton faster. They're going to shoot all over the place, and they're going to put a ton of force on the side of that container, which is going to increase the pressure. All right? So those are those three principles that you can see in action. This law, combined gas law, is the last three smashed together. So it doesn't say anything different. It just allows you to use those three laws in tandem with one another. So it's P1V1 over T1 equals P2V2 over T2. And again, my initial side, what I'm starting with, is on the left. My final side, what I'm ending with, is on the right. When one of those three variables, pressure, temperature, or volume, is held constant, because that's something that you might see in problems from time to time, the combined gas law actually turns into Gay-Lussac's law or Charles' law or Boyle's law, and I'll show you what I mean by that. So if I hold temperature constant, right, that means that it's not changing. I am left with Boyle's law. If I hold pressure constant and it doesn't change, then I'm looking at Charles' law. If I hold volume constant and it doesn't change, now I'm looking at Gay-Lussac's law. So again, if you hold something constant, what that means is take it out of the formula, and then you're just looking at any of the other three. So sometimes in our problems, volume or temperature or pressure gets mentioned, but it's only mentioned in the sense that it's being held constant, in which case you would just take it out of the combined gas law's formula, and you can use the other formulas at will. Next law I want to talk about is the ideal gas law. The ideal gas law, that it states that pressure times volume is equal to the amount of moles of a gas times an R constant times temperature, but only for an ideal sample. An ideal sample of gas, right? So that's going back to our ideal gases, gases that are going to follow these laws exactly and not act weird at all. For this, it's more important in this law than I would say any other law that you have specific units. Pressure is a little bit variable. You could have that in atmospheres or in kilopascals or in millimeters of mercury or whatever. But volume must be in liters, N must be in moles, and temperature must be in Kelvin specifically. Your R value you are going to pick based on the pressure unit. So as a reminder, you have a few options for R. You could use 0.08206 if your pressure is in atmospheres. You could use 8.314 if your pressure is in kilopascals. You could use 63.36 if your pressure is in millimeters of mercury. All right, those are your main three options that you're going to see going forward. The other law, the last law I should say that I want to talk about, is called Dalton's law of partial pressure. And it states that in a sample of non-reactive gases, so gases that are not going to start reacting with one another if they're put in the same place, the total pressure of that gas sample is going to be equal to the sum of the partial pressures of the components of that sample. So basically, like, if I have a sample of helium and argon, and I put them in the same place, because they're not going to react with one another, if I have half of that sample is helium, half of that sample is argon, and I add their partial pressures together, that's going to equal the total pressure of the sample itself, which sounds really easy, and it is. But there are ways to complicate Dalton's law, and I'll show you a couple of those ways in a second. The other thing that Dalton's law states is that partial pressures are proportional to molar quantities. So if 50% of my sample is helium, helium also represents 50% of the total pressure and 50% of the total moles. So it just means that they kind of match together. So let's take a look at a visual representation of what that means. Let's say my total sample over here is a 10 mole sample with a total pressure of 1 atmosphere. I can see in this sample there's 3 different gases in there. I see a blue, I see a red, and I see a green, right? If I were to separate that sample out into its base parts, I would see that part of my sample is gas A, which is going to represent 5 moles of the total 10 and 0.5 atmospheres of the total 1 atmosphere of pressure. The second gas is going to represent 3 moles of that overall 10 moles and 0.3 atmospheres of pressure. And my last one is going to represent 2 moles of the overall 10 and 0.2 atmospheres of pressure. And according to Dalton's law, the formula for which is up here, my total pressure is simply equal to the sum of all my partials. So if I add 0.5 plus 0.3 plus 0.2, I get 1. That is what Dalton's law says. But what I wanted to point out as well is that if we were to break this down into percents, this one, gas A, represents 50% of the sample. 50% of 10 is 5. 50% of 1 is 0.5, right? Gas 2 represents 30% of my sample. 30% of 10 is 3. 30% of 1 is 0.3. And then finally, my gas 3, gas C, is 20% of my sample. 20% of 10 is 2. 20% of 1 is 0.2. So that's what I mean up here when I say that the partial pressures are proportional to molar quantities, is that percentage is going to be the same either way. All right? So now the harder part, picking a gas law to use when you are presented with a problem. The easiest way to do that is to identify which property each number in the problem refers to. And the properties are going to be pressure, volume, temperature, moles. Once you have done that, you've identified every single number and what it means, then you can pick the formula that you have enough info for. So if I go through my problem and I have, a P and I have a V and I have another P and I'm asked about a V, that means I should be picking Boyle's law because P1V1 equals P2V2. I have enough information to use that law. But if I went through the problem and I found a P and a V and a T, but I didn't find anything else, I don't have enough information to use Boyle's law. So I should not pick Boyle's law because it doesn't make sense with what I have. All right? So let's practice that. Practice problem number 1 says a sample of gas initially at 13 atmospheres occupies 4.60 liters of space. If its container is expanded to 5 liters, what will its new pressure be? Okay, so the first thing I'm going to do is I'm going to underline my numbers. I see 13 atmospheres, I see 4.60 liters, I see 5.00 liters, and I am asked a question. So I'm going to underline all of that. ATM is a pressure. Liters is a volume. I see another liters, so that's another volume, meaning that that's probably V1 and that's probably V2. I'm asked a question about new pressure, so that's probably going to be P2, making the other pressure that I was given P1. So now that I've underlined and I've identified my numbers, now it's really easy to pick a law because I just need to go back through my list of laws and pick a law that only has P's and V's in it. So if I go up on my list, that's Boyle's law. Here, P1V1 equals P2V2, and that's exactly the law that I'm going to use. All right? So 13.0 ATM times V1, which is 4.60 liters, is equal to my new pressure, I do not know what it is, times 5.00 liters. And all I have to do is solve that out. So I'm going to do my left side, 13.0 times 4.60, and then I will divide by 5 to solve, and I get that P2 is equal to 11.96, which, by the way, is in ATM, because my initial pressure unit was in ATM, so is my final going to be. And I also am going to have to round for sig figs here, because all 3 of these numbers have 3 significant figures, so I'm actually going to round this off to 12.0 ATM. And that is going to be my final answer. Practice problem number 2. 14.6 grams of oxygen gas, O2, occupies a 2.5 liter container at a pressure of 56.7 millimeters of mercury. What is the temperature? So, I have a few different pieces of information thrown at me. I have grams, which is mass, and I didn't actually talk about mass as one of your possible units. However, mass is easy to convert into moles, which is N. So as soon as you see mass, you should start thinking about converting it into moles. Liters is a volume unit. Millimeters of mercury is a pressure unit. I am asked about temperature. So what I need to do is I need to consult my list, and I need to find a gas law that has temperature and pressure and volume and moles. And moles is going to be your easiest thing to identify, because there's only one law that directly mentions moles, and that is ideal gas law. PV equals nRT. All right? So, first thing I need to do is I need to deal with this gram amount, because I do not have moles yet. I need to find it. So I'm going to take this 14.6 grams of oxygen gas, and I'm just going to convert it into moles. Now, in terms of the molar mass of oxygen gas is what we call a diatomic element, and you're given the formula. So when you look at the periodic table, you're not going to use 16. There's 2 of them there, so you're going to use 32 grams. And that is how you'll get a good conversion into moles. That is going to give me 0.456 moles of oxygen. And that number is N that we'll use in the formula. Pressure I'm given directly, so I'm just going to put that in where pressure goes, 56.7 millimeters of mercury. Volume I'm given directly up here, so I'm going to put that in where volume goes, 2.50 liters. Moles I just calculated, so I get to put that in, 0.456 moles. R value is next. Now remember, R values are going to be picked based on the pressure unit, and our pressure unit is in millimeters of mercury. So I should be using the R value for millimeters of mercury, which if we go up really quickly, that one is going to be 63.36. So I go back down here and I use 63.36. I'm not going to stick the whole unit on it because the whole unit's a mess. And finally, I am asked about temperature. So that thing is going to be what we're solving for. Now that I know all of that, it's just a clear plug and chug. So I'm going to plug all of that into my calculator. And I get a temperature of 4.91 Kelvin. Yes, I know that Kelvin is the unit that has to pop out in, because again, we covered in the last video that temperature has to be in Kelvin. And since I know that, that means that my temperature has to pop out in Kelvin from this formula. Last problem is going to be a sealed vessel contains 65 grams of neon gas and 35 grams of argon gas. If the total pressure inside the container is 15.0 atmospheres, what are the partial pressures of each gas? So there's a couple of interesting pieces of information here. We're given two values in grams, which is great, amazing. We're given two values in grams. We are given a total pressure, PT, and we are asked about partial pressures. Now, the only gas law that asks about partial pressures or talks about partial pressures at all is Dalton's law, which states that total pressure is equal to the sum of all the partial pressures. Now, in this case, we only have two gases, so I only need pressure 1 and pressure 2. So we're going to have to do a little bit of thinking to solve this problem because we're not given any information about the partial pressures. We're only given a total. But what we are given is a gram amount for each. All right? So that gram amount is going to help us to figure out the percentage that each of these gases relates to in terms of the total pressure of that sample, right? So, looking at this, since I'm seeing grams, the first thing I want to do is convert into moles because we know that each element weighs something different on the periodic table. And so moles is the way you can compare amounts in a clean manner. So I see 65 grams of neon, so my first step is going to be convert that to moles. On the periodic table, neon weighs 20.18 grams. All right, so plugging that into my calculator, I get 3.22 moles of neon. My other gas up here is 35 grams of argon. On the periodic table, argon weighs 39.95 grams. So plugging that into my calculator, I'm going to get 0.876 moles of argon. Okay, so what I'm going to do next is I'm going to figure out the percent of total that I have. So the first thing I need to do is I need to add to get my total amount of moles. So I have 3.22 moles of neon plus my 0.876 moles of argon, and that is going to give me total of 4.096 moles total. And that is the whole sample. So with that information, you are going to figure out the percent that neon represents of your sample and the percent that argon represents of your sample. And we're going to do that by simple division. All right, so neon is going to represent 78.6% of that sample, or 0.786. And I'm going to keep that as a decimal because it's going to be more useful to me that way. Argon is going to be done exactly the same way, and we're going to divide 0.876 divided by our total, 4.096. All right, so then that number is going to be 0.214. All right, so again, we're keeping those percentages in decimal form because what we're going to do is we're going to end up using those to multiply by our total pressure to get our partial pressures. All right, because in our problem up here, we were told that our total pressure is 15 atmospheres. And I know based on what Dalton's law says that our percent of total in our moles is very closely related to our percent of total in atmospheres. They are proportional to one another. So I can take that 15 atmospheres of my total pressure and I can multiply it by each one of these to get my partial pressure. So if I multiply that number by 0.786, that is going to give me my partial pressure of neon. And that is going to be 11.79 atmospheres of pressure. And of course, we're going to round that for sig figs. My initial pressure was given to me with 3 sig figs. It was 15.0. So I'm going to round that off to 11.8 atmospheres. And that is my partial pressure of neon. And that's how you would abbreviate that. I'm going to take that 15.0 atmospheres and I'm going to multiply it by 0.214. That's going to give me 3.21. And in this case, we're going to round for decimals because this number and this number have to add up to exactly 15. So I'm actually going to round that off to 3.2 atmospheres. And that number is going to be my partial pressure of argon. So again, Dalton's law, it sounds simple on the surface that if you just add, you can get to total pressure. And sometimes that's true. But sometimes it requires a little bit of thinking to use Dalton's law, and this is one of the ways to complicate it when you're given grams instead of pressures directly, but you can still use that information to find what you need. So if you're going to have any issues with this, please feel free to ask me about it in class.